Good morning. Well, the snow has dissipated somewhat, but it's still chilly here in New York City. Now, I'm going to continue talking about the celestial sphere, aspects of astronomy. Call it aspects of astronomy number 1. Now, on the last occasion, I started looking at equatorial coordinates, right ascension and declination. Right ascension, it's like celestial longitude. Declination, celestial latitude. Now, where is it measured from? As I discussed, we put the Earth with its equator and axis inside the celestial sphere. And the celestial sphere is a projection, contains a projection of the Earth's equator and a projection making the north celestial pole and the south celestial pole as points on the equator. Okay? Now, as the Earth revolves, this celestial sphere appears to revolve to us, but we're actually revolving. Now, we're doing more than revolving, and that's what complicates things. When we want to figure out time in terms of the sun as compared to the fixed stars, it gets complicated and different. Not only that, when we want to make coordinates, it gets complicated and difficult because nothing is fixed. Now, we can base our coordinate system on the equator, the celestial equator, and then we get celestial, let's say, declination, right? And a star will have a certain altitude in the night sky, altitude above the celestial equator, and that goes from 0 to 90 in the case of declination, and negative 90 south of the celestial equator. We discussed this already. Now, I didn't get around to doing examples of showing you where stars might be, but you know, you can get that on the web. I'm just doing a basic for interest introduction to this because I'm not really an astronomer. All right, then the next thing, right ascension. Well, the right ascension works like longitude. But we need a prime meridian. For our longitude on the Earth, we choose the meridian, or great circle, that goes through Greenwich, not Greenwich, Greenwich in London, the Royal Observatory in Greenwich, down there on the Thames in London. That's called the prime meridian, and it's 0 degrees longitude in the case of the Earth. Now, in the case of our celestial coordinates, the equatorial ones, the beginning of our right ascension is going to be here. Where? Where the ecliptic cuts the celestial equator. It's called the vernal equinox. That's the symbol of a ram. The first point in Aries. What does that mean? Where Aries as a constellation begins. I'll talk about that as a while too. You don't really need those stars up there to designate those constellations. They're just boxes, right? With a certain angle. Now, you can measure the angle in degrees, all the way around from 0 to 24. Did I do that right? No, I meant to do it this way. All the way around on the celestial equator. Or you can measure, that's what I do actually, I use degrees. But astronomers like to use hours, because another way of looking at declination is that for the 21st of March, is it? I forget. The declination is the time behind, the number of hours behind the sun, the time behind the sun. So a star that's 2 hours behind the sun will rise 2 hours after the sun rises. That would be a star with 2 hours right ascension, and so on. It kind of makes things easy if you're an astronomer. Now, okay, so all this stuff gets extremely complicated due to the motions of the Earth. So I'm just going to very quickly talk about some other coordinate systems. All right? I want to talk about what the coordinate systems that I would like to use. Sidereal, okay? Sidereal, well, I think that astronomers could well be in the process of renegotiating what coordinates they're going to use. So, first of all, I want to show you where things begin to get complicated. So, equatorial, ecliptic, and sidereal are 3 types of coordinates. but there are many others. There are sun-centered coordinates, there are moon-centered coordinates, there's altitude and azimuth coordinates, and so on and so forth. But as the night sky is moving all the time, and it has complicated motions, one coordinate system will always have some benefits over another, depending on what your requirements are. That's a long story. Now I'm going to list the motions of the Earth first, and then I will discuss them. Well, it's really the Earth-Moon system, because the Earth-Moon system has a centre of mass, which is called the barycenter. We'll talk about that in a minute. Now, the first one, of course, is the rotation about the axis. 24 hours is what it takes, and that will allow us to define the 24-hour tropical day, or the hour with 3,600 seconds in it. And it varies a little bit. There are variations in that, depending on where the sun is in its orbit. And the next one is the orbital motion, and it's approximately 365.25 days. I was trying to look up the exact time, or at least a more exact figure, and I just couldn't find it so quickly. So the orbital motion, the Earth goes around the Sun. Now it goes around the Sun in an ellipse, so there are variations in that motion as well. I'll come to that in a minute. Now the next motion is precession. Actually, first called precession of the equinoxes. The equinoxes rotate around at the rate of, I think, 1 degree every 72 years or something like that. All right then, and eventually they complete a cycle. Now all tops execute precessional motion. Precessional motion is accompanied by another motion called nutation. That's done by tops. Rigid bodies. And the equations of motion of rigid bodies, actually I'll do a class on that, are described by the Euler equations. Very complicated little equations. The Euler equations involve moments of inertia and motion of rigid bodies. But tops execute precession. They spin on their axis and then they have a wobble. But there's another one that they do as well. I'll talk about that in a minute. The other motion associated with precession is called nutation. Now, Hipparchus in around 129 BC noticed first, at least that we can remember that's recorded, precession of the equinoxes. Now, he didn't know why that was happening, but that was explained by William Gilbert approximately, sometime, let's say, 1470 or something. In the famous book De Magnete, A Man Before His Time, followed by Kepler, very closely, by the way. I could say a lot about that, and today I won't bother. So, he said that it's the same precession that exists in the topular motion, I use that word for tops, that causes this precession of the equinoxes. Precession of the equinoxes. So precession, two things. Precession of the equinoxes, precession of the top, they're both related. Mutation is a kind of a wobble. Now, there's another one. The Earth and the Moon have a center of mass about 4,000 kilometers from, 4,000 kilometers from the Earth's axis, something like that, 3,000, I don't know. But the Earth doesn't go around on its own axis. It goes around with this little bit of a wobble. As it keeps going around in its orbit, this wobble shows up as an extra motion. Now another motion, let's see what I could put in. The Milankovitch cycles. Now the Earth is in ellipse. Sorry, the Earth's orbit is elliptical. Well, wait a minute. At present, it varies between 94.5 million miles and 91.5 million miles approximately. At some point, it becomes almost circular. This has an effect on the seasons. Milankovitch motion, this was discussed only as recently as the 1920s. So there are 6 motions. Rotation of the axis, orbital motion, precession, mutation, wobble of the barycenter, Milankovitch. What else could I put in there? I had 7 the last time. But that'll do us for now. So let's look at a little bit more closely at these motions. Rotation about the axis. That's a pretty easy one. But there's a complication. The complication is that in the orbital plane, the Earth's axis is not vertical, it's tilted. So that results in the Earth with the northern hemisphere facing the sun in summer and facing away from the sun in the northern hemisphere winter, and vice versa for downstairs. There is also effect due to this distance because the orbit is an ellipse. This is an exaggeration. So at perihelion, the orbital radius is approximately 91.5 million miles. And at aphelion, is 94.5 million miles, and we generally say that the average orbital distance to the Sun is 93 million miles. But this difference of 3 million miles makes a difference to the amount of heat that the Earth will absorb from the Sun. Due to the inverse square law, it's sizable, right? That means that if you have a summer in the northern hemisphere over here, compared to over here, right? There's going to be a weather difference, and that's food for thought for a whole class. So that's the orbital motion. Let's look at precession now. Now they're the 2 main motions. If I want to work out time, a thing called sidereal time, I can approximate it just by considering those 2, because the next motions are small. Now the first one I'm going to look at is precession. Now let's put the Earth's axis in like that, and the Earth is going to be moving anti-clockwise if you look down on it. If you look down on the Earth with the North Pole there, the Earth is turning anti-clockwise. That ensures that the Sun, as we know, rises in the east and sets in the west. Okay, so what's precession? Well, all tops, here's a top. And if you spin a top and it starts rotating, we have the first motion of the top as being the rotation. So the Earth is a top, right? It's tilted on its axis, but that's a separate idea. This is the axis of rotation of a top rotates about its own axis, this one. So if you're rotating a top, this rotation is called precession. The Earth's axis, so we have Polaris at the top of it at the moment, it also has a precession. And that precession generates a cone. This cone, this tip of the cone, the cycle that the axis goes through. So if we're at Polaris right now, Polaris being a North Star, 12,000 years from now it will be Vega. The pole of the Earth will be pointing towards Vega, a different star. And in between, who knows? It's approximately 26 or 27,000 years, I forget. For this cycle to take place, 26,000, let's say, years. Now that makes a big difference to weather on the Earth, but it also makes other difference. Here's an example. Okay, there is an observatory in Ireland called Newgrange, and it has a passage way down deep, and the observatory, by the way, looks like it was made yesterday. It's an underground observatory. Archaeologists can be crazy sometimes. Everything for them is a tomb, and this was supposedly a tomb. It's not a tomb. And then down at the bottom of the tunnel, on the solstice, the sun can get its sunlight all the way down into the main chamber. In the main chamber is a huge stone bowl, concave. Now, I haven't heard it said, but oh yeah, when the sun comes in on the solstice, it lights up the ceiling. But it would do it even more so if they put water in there. That sun would be reflected onto the ceiling. And it does it very closely, but it misses it by about 7 minutes. You know, this event happens 7 or 8 minutes past midday on the summer solstice. That is the lighting of the tomb. And people say, well, that was pretty good building anyway for 5,000 years ago. But wait a minute, 5,000 years ago? That's a quarter of precession. If you take that into account, then the Earth's axis will have tilted a little bit, and the light will shine exactly, or at least more closely, on this magic bowl. And at midday, closer to midday, 5,000 years ago when the observatory was first built, the light would hit the roof, the center of the roof, much more closely. All right, so that's the effect of precession. Now, precession of the axis here results in precession of the equinoxes. That means day and night are of equal length. At one particular day, let's say the 21st of March right now, but you know, in 500 years' time, it could be the 22nd of March, 1,000 years, 23rd of March, and so on, over that 26,000 year cycle, precession of the equinoxes. Now, nutation. Nutation is yet another complication of a motion. Okay, let's make a top that looks like this. And let's give it an axis. So a top rotates that way. We put all the mass in here. So it's spinning. The axis of the top rotates according to the precession that I told you. But there's another one. As it's precessing, it also wobbles. The tip of it goes up and down. I'm sure you've seen that, yeah? Now, it could go up and down in a sinusoidal cycle, or it could do something like this. Well, the Earth is no different. It has its own wobble of this rotation. The Earth is doing this, all the way around in cycle for 27,000 years, and that's called mutation. All tops do it. Oh, it's going to get more complicated than that. Remember I said that the Earth is not just the Earth, it's an Earth-Moon system. So that mutation is not so simple to figure out due to the complications introduced by the Moon being dragged along with us. So the next thing we look at is the wobble of the barycenter. Oh, what's that? The barycenter? Okay. We'll take a sphere and we'll join it to another sphere, and they have masses m and m, and a rod, which is massless, connects them. Now we put them into a rotation. We throw them. So we throw them across the room. But really what we track is, when you go across the room, is the motion of the center of mass. The center of mass generates a parabolic path, but the individual masses do not generate a parabolic path because they're twisting. This one would generate a path that goes like this. And so with this one, but with a bigger amplitude. So this is the path of these two guys separately. This is the barycenter. The barycenter moves on a smooth curve, but the objects don't. They're doing a wobble. What does the Earth do? Same thing. Now I don't know, I think is it 22 days or something that this cycle happens, the time it takes for the Earth and Sun to mutually orbit each other. Is it 22 days? I can't remember. So let's suppose we have the Earth's orbit. The Earth's orbit, is it in this case an exaggerated ellipse with the Sun at the center? And here is the Earth-Moon system, once again exaggerated. And so on and so forth. The barycenter follows the orbital path, which is the ellipse, but the Earth is doing this. As you can see, it has a little amplitude and a period. It has another cyclical motion. All of these things complicate where we are going to have to look on the celestial sphere and at what time to find a particular object, such as a star. Where is it going to be? What are its coordinates going to be relative to the Earth? But these things also complicate time. Now the last motion is the Milankovitch cycle. Now, if we take the eccentricity of the Earth, we could write a little equation and say that the actual orbital motion, the radius of the Earth's orbit, the average one, averaged out, is circular if this eccentricity is 0. But if we make this a bigger factor or a smaller factor, positive or negative, we can change the eccentricity up or down, like this or like this, a wobble. So that the Earth's orbit is going from ellipse to circle to different ellipse to circle to ellipse to circle to over a period of 100,000 years. It's yet another periodic motion. Now there was one other motion of the Earth that I talked about when I did this talk first, and I can't remember what it was because I had 7, I know that. But this is good for now. So let's see what we can do now with regard to time, sidereal time. Actually, let's not do time. Let's stick with the coordinates. I said I'd look at other coordinates. Right ascension and declination, let's call them equatorial coordinates. Let's do a different coordinate system. Now I'm sorry I'm not doing the best circles for you guys, because when I put them on the board I don't have time to correct them. Now, this red circle is the path of the sun across the night sky, the sun. The sun will move on that path. I don't mean per day, I mean throughout the whole year. It appears in a different place on the cycle. And it actually, specifically, it appears in a different constellation. Now, if you were looking at the sun from the Earth, and on the far side, you're in the constellation Aries. Aries down here. That's the ram symbol. That will be the beginning of the counting of right ascension. And right ascension is an angle based on this equator, hence equatorial coordinates. Now, unfortunately, what happens is this guy, what we already said, precesses around the place. It precesses over a period of 27 years, so it's moving. So another way to counteract this problem is don't set up our coordinate system with poles north and south equatorially. Choose the ecliptic as the center, so that the constellations of our zodiac now lie on what is our celestial equator. The zodiac, yeah, I don't remember all their names, but there's 12 of them, and they take up 1/12 of a circle. That's 30 degrees each constellation, right? Forget the idea of the names of the constellations and just be a scientist. They're boxes. They're boxes on the celestial sphere of a certain width, 30 degrees. And each one of those 30-degree boxes corresponds to an hour. And there are 12, well then I guess that's wrong. Must be 2 hours. Whatever. There are 12 constellations in the zodiac. Am I saying this the wrong way? I'll come back to it. Anyway, one way or another, if your sun is blotting out a particular constellation, and it can blot out all of them, suppose the sun is in the way and you can't see Aries, or whatever it is there, then that constitutes like the star sign Aries. The sun is in Aries, and so on and so forth. Now we're in Aries. I think we're going into the age of Aquarius, the hippie song. That's coming up in, I think, 2200 or something. You could look it up on the web. But we're moving into the age of Aquarius, out of whatever we're in now, I don't know. I have it written down somewhere. But the coordinates that I like are these ones. These are the best coordinates. And people don't use them. Because even ecliptic coordinates have this precession going on in them. Sidereal coordinates. Sidereal coordinates I like them a lot. I think they're nice. Bruce for sight. You hear a lot of sidereal things. Sidus, star, Latin word for star. Anything sidereal is based on the stars. This coordinate system doesn't care if the Earth is there or not, or the sun. It's just, well, if we just, assuming we pick our position where the Earth is, this coordinate system has on it just the fixed stars. Now in the, which one? The ecliptic coordinate system, they still chose the vernal equinox to be the origin. And that's moving, right? But in sidereal coordinates, you take a fixed star. Now, one star in Virgo, according to one guy, is a good choice. Let me see who that guy is. Okay, I'm no good with notes. I'm no good with notes today. But if we take the zodiac, this is the ecliptic, right? We forget about the tilt of the earth or anything, but we just take a star, one star in Virgo. I think it's Pi Virgo is the star that some guy suggested we should choose. So that would be the constellation Virgo, and the next constellation, and the next constellation, and the next constellation, and so on and so forth. Let's find those constellations. Okay, so if it starts out with Virgo, I do it in abbreviation, Capricorn, Aquarius. That means we must be in the age of Capricorn. I don't know what this is. I wrote it in brief. Taurus. Gemini, Cancer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I got them. Now, incidentally, when you label stars in the constellation, you go alpha, beta, gamma. So, Pi Virgo, that's going to be a star that's not that bright in Virgo. Alpha Virgo would be the brightest star in Virgo. Bright star in the constellation Orion is Betelgeuse. I don't carry a lot of the names of these stars and constellations around in my head, by the way, though. Anyway, so what we do now is we take these stars, they're all fixed. For example, Ursa Major is up here. And these two stars point to Polaris. Polaris is pretty close to being on the axis of this coordinate system, but not exactly. And the Southern Cross is way down here in the southern hemisphere, and all the other constellations, Cassiopeia, wherever they are fixed and nothing moves. Each one has a particular coordinate. It's going to have, every star is going to have an angle of, let's say, declination and altitude. Which is going to be still a declination. And whatever way you choose to put it in, I like degrees. So if this star is going to be, let's say, on this meridian, that's the number of degrees it's got anti-clockwise of Virgo, the sidereal coordinate system. Okay? I'm going to stop that talk for now. The next talk will be on time, sidereal time, because this is the way it works. When the sun rises and sets, it takes 24 hours to do it. You mark a point on your window, and you're in bed, and you put a little sight. You need two things to sight. And you look out here and you see a sun is on the window ledge at 6 o'clock in the morning, the limb of the sun, that's the edge of it, at 6 o'clock. Now, when you get up at 6 o'clock the next day, you expect the sun to be right there in the same place. And it will be, give or take a couple of little motions due to the other factors, but the rotation of the Earth will be 24 hours. We take a star now, and we do the same thing. We sight on a star, and we wait for it tomorrow night. We'll see it at 9 o'clock. Bang! Now, 9 o'clock tomorrow night is going to be 24 hours away, whereas the star is going to be higher up a little bit because it came there before the 24 hours. Specifically, it came at approximately 23 hours and 56 minutes, sidereal time. That's because the rotation of the Earth with respect to the fixed stars is quicker. It's got the rotation of the Earth plus the orbital angular velocities, and you can add angular velocities. So if you have, let's say, an angular velocity of 10 radians per second plus another one of 1 radian per second, the two of them are going to be added together 11 radians per second. You can add them together and you get the spinning going quicker, so you get a different time for stars. Star time is called sidereal time. Okay, that's it for today for this one. Somebody asked me to do some talks on basic electricity for high school and maybe elementary college. They wanted Ohm's law done, and they wanted, what else? Kirchhoff's rules. I'm going to do that in the next class.